Right, here we go, second session. Okay. Oh, I shouldn't be doing that, sorry, I know. But on the module itself, which I hope you can see now, in the sessions, my stuff, water quality, and conventional treatments, so there's lots of things I can see that you can't see, but there's a tab on water quality. If you go in there, then there's a file that I just sort of cobbled together some stuff on water quality, the general sort of things, solids, BOD, some of the inhibiting substances, toxic substances, and so on. So you could maybe have a look at that. The other thing is this. I'd really like to direct you to the WHO guide on water quality. So I tried the link earlier on and it worked, but sometimes the link doesn't work. So we'll see what happens. Oh, it does work. So this is really quite something. It's a fairly large document. I don't want to open it now, but you can see here 564 pages. So I like this because it includes all aspects of water quality. Of course, the focus here is on drinking water quality, and my topic is on wastewater, but still we're treating wastewater to a large extent so that we can safely release it back into the environment. So it will eventually affect drinking water quality. So the thing with this is, if you're interested in water quality in general, whether that's particular substances, chemical pollutants, BOD, down to really wealth of detail on individual pathogens, this is excellent. So you just look at it, you go through the index, and you find the stuff that you want to do to look at. So I think this is much better than, say, Wikipedia or something, because maybe got a bit more, how should I call it, kudos to it. So if you want to find out about any particular substance or type of contamination quality criteria, have a look at the WHO stuff. I think it's great. So I bring this back over because then we could go back to the slides. Anyway, okay, so last time I talked generally about introduction to water, wastewater quality, why we want to treat it, and so on. And I think I ended up with this here slide, where I sort of tried to introduce the first main overview of a wastewater treatment plant. So it's very similar to what you have. Ooh, let me just change this to that. So it's very similar to a wastewater, to drinking water treatment plant. The stuff comes in, and I'm repeating myself from last week. It goes through a screen where you get the really big coarse stuff taken out that can be taken out easily, and also that would maybe damage the equipment and machinery on the treatment system. Then the water flows through a grid separation where we have the first time gravity doing its work. So large particles, grit, would get separated out and just fall to the bottom, get collected as the inert waste. Then we go to the primary settlement, and that is really the first time that you have real, I would say, wastewater treatment happening, because this is where the organic solids get removed. And I use the term organic in a way that is not correct, because it's neither chemically correct, because there might be stuff in there that is inorganic, and it also isn't correct in terms of soil association and so on. It does not mean that this stuff is good for your food or good for the world. I'm just saying it is biological material, so poop, banana peel, that sort of stuff. So this stuff gets collected by gravity, collects to the bottom of these tanks, then flows over into the biological process where we have the bacteria doing their work, and you have more stuff on the bacteria later on in the session. After we've grown all these bacteria here in the secondary treatment, we have to remove them before we release the water into the environment, and that's why you have secondary settlement, where nothing much else is happening than that you collect the bacteria, discharge them. So either the bacteria get put straight into sludge treatment or something, or part of the bacteria could also be recycled in the biological process. That's not shown on the slide, and I should maybe just correct that, sorry. So what you could also have is here a sort of flow. Oh, now I have to see if I get a arrow on that. Oops, not very good. Where part of the activated sludge is recycled, and you would see that referred to, oh, my handwriting is terrible on this thing, as return activated sludge. So you generate the activated sludge here in the biological process. You collect it in the secondary settlement. Most of it gets discharged for sludge treatment, incineration, whatever it may be. But some of it you also have to return into the process, because the water flows through this plant faster than the bacteria grow. So if we kept the water just openly flowing out, then you wouldn't have any bacteria left here in the biological process to actually do the biological process. So again, some return activated sludge goes back into the front end. Of the water itself that overflows, it could then either go directly out into the river or wherever, or you could have tertiary treatment. And last week I used the example here of, not last week, last session, I used the example of celery and fried Mars bars. So it could be something as simple as that, to have a secondary or tertiary rather biological treatment system. Or it could be any of the fancy stuff that you learn primarily in Chachansk sessions. So UV treatment, I don't know, titanium dioxide, oxidizing substances, ferrate, all the sort of stuff, membrane filtration, all that could happen in tertiary treatment, and we get to that later on. So for the moment, for my slides, I'd like to concentrate just for today anyway on this sort of general layout of the plant. But maybe remind you of one other thing first, and that was that I said that wastewater treatment plants in general really only do three things. So the one thing is that they remove solids. So you have the solid removal is one of the main process operations here, and that's what happens here: grid separation, primary settlement. Primary settlement in particular is where you remove the solids, the organic solids that we flush down the toilet, the kitchen sink, and so on and so forth. Then the next thing that it does is it removes BOD. Oh, let me get back to this. So that's biochemical oxygen demand. That means that's all the stuff that's in the water in soluble, dissolved nature or finely dispersed, so it doesn't settle out. And these solids or soluble materials that create oxygen demand in the receiving water, you cannot get out by sedimentation, or certainly not easily. So that's where you have the biological process. So the main function of the biological process is to remove the BOD. And then the last thing really that you also have is, oh dear, nutrients. I'm getting to the end of the slide. So nutrients are primarily nitrogen, possibly phosphorus, that get taken out. So some of the nutrients get just taken out with the material that you settle out here, because there's some nitrogen in these substances. And some of the nutrients are removed in the biological process. And that is actually almost tertiary treatment. So the biological process that we have in the conventional treatment work is to get out the BOD. But what it also does, if you run it properly, is that it removes some of the nutrients. It will only remove in a conventional treatment plant nitrogen. And only if you do it right will it remove it correctly. If you wanted to remove phosphorus, you would have to get into the tertiary treatment. So you see already that even for very box standard fertilizers, the stuff that if you go to a new gardening shop and you buy a bag of fertilizer, it will have NPK in it. So of that, only nitrogen is normally removed. Phosphorus, you already have to be a bit clever, and the other stuff, then it gets really quite complicated. So the more you go into the detail of the treatment, then you have to go into tertiary treatment, because I keep saying the same stuff. Wastewater treatment plants are actually quite simple, and they're not particularly sophisticated, and they don't do very much other than to take out solids, BOD, nutrients. So enough talking about this, because really That's what it is. In text, the order or the main bits to remember are preliminary treatment removes the big solids, grit, stormwater, oil, fats and grease and that sort of stuff. Then you have what is commonly referred to as the primary treatment. That is working by sedimentation. There you remove the settlable solids. And settlable is not really a technical term, but it basically means you remove the solids that will settle out in your particular treatment works. There will still be solids in the water that won't settle out, and you see them as distinct solids if you look under a microscope. But you have, of course, also solids that are dissolved, like sugar in a teacup and so on, that will never settle out. So that stuff goes transferred over into the secondary treatment, where we have biological treatment. And this is where you remove the dissolved organics, or those that are so finely in suspension that you cannot get them out by physical treatment. Tertiary treatment will be used only if the final discharge quality that is given to you by the environmental regulator requires this. So there you could remove more BOD, you could hold back more bacteria, hold back more solids, or you could go into the finer detail of targeting particularly toxic substances, particular nutrients that are of concern to the environment where you're discharging and stuff like that. And then you have the sort of separate process almost of sludge treatment. So if you think of the sludge that comes off a sewage works, as it comes off the works, it might have something like 8% solids. So the sludge is primarily water, 92% water or thereabouts. So the first step normally is that you dewater it, you reduce the water concentration, so you're not dealing with so much water, but you're dealing with the stuff that you actually want to deal with. And then you have the options of, like it says there on the slides, stabilization or straightforward disposal or digestion. So one thing that's always taken quite commonly in most places in the world, I think, is this here digestion, which simply means that you consider the sludge as another organic waste source. And this source, and we get back to that later, is relatively uniform. It lends itself to anaerobic digestion. So you put it through anaerobic digestion, you reduce the polluting concentration of BOD, and you get a bit of energy out of it. But again, we get to that later on. This stuff here, stabilization, that's, I don't know, that was probably slightly out of date, but people used to try all sorts of things with it to use the material in the sludge, maybe to build bricks. So you could dry the stuff and then you could mix it with cement and concrete and stuff, and maybe make breeze blocks out of it. You could put it maybe into soil as sort of structural components of soil, but that's a bit of a tricky issue because it's really disposal of waste. And then you have straightforward disposal. So stabilization and disposal will definitely require dewatering first, because you don't want to stabilize water and you don't want to dispose water, really, ideally. You want to dispose and stabilize the bacterial biomass that's in that sludge. Digestion does not need dewatering much, maybe a little bit of concentration, but it works okay at 10% or so solids. So the disposal option is really the one that is less and less an option, because in Scotland in particular, or the UK, much of the sewage sludge used to be just disposed of at sea. And the argument was that it's good nutrients for the sea, it makes the fish grow bigger, and the sea is so big that it doesn't really make much difference. Because if you think of it, the wastewater that we're treating and discharging into the rivers, that also eventually goes into the sea. So the sea is actually the final disposal ground for most of our wastewater. But obviously then that was outruled, and gone are the days where I think in Glasgow there used to actually be a ship was quite popular with pensioners in particular. They just went out 2 or 3 times a week, and they did a big sweep sort of around the Ayrshire Bay, and it basically just took the sewage sludge of the city and it spread it into the bay. So that's not allowed anymore. The next form of disposal that was then used tended to be landfilling. But with the European directive, I don't know where this is going now, but new landfilling of organic material is not an option anymore, because landfilling of organic material tends to lead to methane generation. So it gives you global warming gas release, which is not a great idea. So the really only options that you have is digestion first, get as much as possible of the organic material out, then maybe dewater it and then see what you can do with it. Stabilization, I don't know. So the big thing that's missing here is, guess what's missing? Does anybody want to say something in the chat? What's happening a lot these days with sewage sludge? I mustn't call it this, but it is. Incineration. Yes, you have, Phyllis, you have the much more technically correct word. Thermal recovery, I think, is the word, because you mustn't call it incineration, because that goes together with all sorts of connotations of just putting fire off it and creating lots of bad smoke and air pollution and so on. So we use thermal recovery a lot, which of course means also that you might first dewater the material. So again, water doesn't burn very well, so you put it through filter presses and all sorts of things. And what's left, you then incinerate. So I'm babbling a bit here now, but if you are motorists and you drive on the M74 on the Glasgow South towards the southeast, actually doesn't matter which way you drive, but at some point you will have a landfill on one side of the motorway, and you can see the big pile and all the the pipes and so on. On the other side, what you don't see quite so much is the sewage works next to a crematorium, next to a sludge pelletizing plant. So that is the location where most, if not all, of Glasgow's sludge and the greater Glasgow area is dewatered and then dried to form pellets. And these pellets are meant to be incinerated, or rather thermally recovered. In Scotland as a whole, there's about 50% of sludge going to land and 50% of sludge being incinerated. For the UK as a whole, the balance is more like 80% going to land and 20% being incinerated. And we can come back to that later, but within Europe, there's quite a difference in what to do with the sludge. So in Switzerland, for example, all sewage sludge is to be thermally recovered, whereas Sweden, I believe, still has a policy to try wherever possible to recover all sewage sludge through land application, because they're saying that there's a lot of good nutrient in the sludge, particularly nitrogen. In order to get this nitrogen, normally you have to spend a lot of energy to get it out of the air and make it into nitrate and ammonia and these sort of things. So why should we burn the stuff? So within two, if you want, European countries, there's two completely opposite views of what we should do with the stuff. One country says we should burn it all because there's so much stuff in it, we don't quite know what it is, we don't know what the danger is. Let's just incinerate it, that's safe. On the other hand, they're saying, yeah, resource recovery, put it to land as much as possible. I think as we're going along, and as there's more and more awareness being generated and accepted, I think knowledge disseminated on all the substances that are in sewage sludge that we don't quite know, and that we don't know how they behave in the environment, but we do know we can't remove them. I think the tendency is going towards incineration. And I say incineration here rather than energy recovery because it's not really the energy. I know that's the technical, that's the correct word. But the important thing with incineration is the high temperature. You need to get really high temperature so that all these man-made substances, the pesticides and inhibiting substances, stuff that affects biological functions, that needs to be destroyed. and you destroy it by using high thermal conditions. So why not call it incineration? But that's just my point. Anyway, the big thing that was missing here was incineration, and there we have it now. Good. So that's in a nutshell, what happens in wastewater treatment. I'd like to go very briefly into the primary treatment, but you do much of that with Jachan anyway, on his part of the module, and then start looking at the secondary treatment. That's all for today. So sedimentation, I mean, yeah, you use sedimentation to remove suspended solids. So again, it's the suspended solids. It's not easy to say what are suspended solids. There are some criteria that you use for analytical sciences, where you might say a suspended solid is anything that's over, I don't know, 0.6 micrometer or something like that. But that works on the basis that you have a fine lab setup where you have a defined filter and you have all the time in the world to squeeze water through a filter and let the filter retain all these solids. So analytically, suspended solids, this sort of stuff is 0.6 microns. But I'm saying that that's only for analytical purposes, because what you can remove when the sewage works depends really on how much dirt there is and how much time you have, how big your sedimentation plant is. So these solids, they stay in suspension because the water moves, and the larger they are, the larger or the heavier they are, the more they have a tendency to fall to the ground. So the sedimentation is the more efficient, the larger and heavier your particles are. The more you have really finely ground up material, the harder it is to get sedimentation to work. So what you need for sedimentation is this: you need still water, because you want no water movement, because the water movement will keep these particles in suspension, will constantly stir them up. So you leave the water standing, and then the solids settle out, and that's your sedimentation. There's various designs to this. It doesn't really quite matter which. It could be like a sort of a conical shape, or it could be just a flat bottom that has a bit of an incline, like a slope. It could be roundish things, square things, heptagonals, I don't know, whatever. At the end of the day, it all depends on how much time do you leave the stuff, how still do you manage to get the water, and how long is the distance that the particles have to settle to the ground, because only if they hit the ground will they be settled out. So this is not just the physical parameters here, but also a question of cost and space and all that sort of stuff. And for my part of the module, just to highlight this again, we're talking about simple or plain settling. So in a primary sedimentation plant, you would not normally have any addition of coagulants or other such things. That is what you discuss very much in detail with Jachan for the drinking water treatment, that you add coagulants first to enhance the sedimentation. So for wastewater treatment, it tends to be sedimentation without that chemical assistance. I think this you've done already, yeah? Or if you haven't, then you will do it with Jachan, the sort of Stokes' law on the terminal velocity of a sinking particle, all sorts of stuff, blah, blah, blah. And again, this I think you will or you have already seen with him, by him. It all comes down to the water travels through the sedimentation tank at a certain velocity, so it stays in the sedimentation tank for whatever, 2 hours, to give an argument. And whilst the water is very slowly moving through the sedimentation tank, the particles sink with their terminal velocity. So if there is enough time for the particles to traverse the distance from where they are to the bottom of the tank in the time that the water stays in the tank, then they will settle out. If the water flows faster through the tank, then the particles can settle to the ground. Then the particles will not settle out and they will overflow. And that's really all it comes down to. And then there's some jiggery-pokery about, where does the water enter? It doesn't enter normally at the top. It enters here and it sort of gets filtered through and enters the tank on a broad area, so we do not create turbulence, which of course means that a particle that starts the tank here has all of this distance to settle, whereas a particle that enters to the bottom hole here only has that distance to settle, which means that you get a non-uniform sedimentation efficiency. So depending on where the water enters the tank, here you have a much lower sedimentation efficiency because the particle has to travel all this distance, whereas there you have a very high sedimentation efficiency because the particles only have to travel this short distance here at the bottom. Anyway, I think as the rule of thumb, you say something like, if you calculate this, then you only get about a third efficiency, and maybe you have to size your tank 3 times larger than what this pure law would tell you. But again, you'll do that with Jachan. So I refer to that quite a bit in this context. So all that you will do with Jachan about sedimentation efficiency calculations also applies to wastewater treatment, because it's the same thing. It's gravity pulling on the particles whilst they get carried through the tank, and only if they hit the bottom are they settled out. So that is, in a very small nutshell, the primary sedimentation. So refer to the stuff you do with Jachan on it, but it really is nothing other than particles in water reaching a terminal velocity, which is much, much slower, obviously, than the velocity of a Coke can that you throw out of the 15th-story high-rise building. That settles much faster. So we really are talking, therefore, normally of a residence time in a sedimentation tank of about 6 hours. Could be slightly less, could be slightly more, and we won't be able to go to a tank because of all this thing, but I have some photos for you in a later session. When you go and see one of these sedimentation tanks, it does appear as if the water is standing. You don't actually see any movement of water with your eye, and that is simply because that's the plan of the whole tank, is to keep the velocity of the water as close to zero as possible, so that there is A, no turbulence in the tank, and B, the water stays in the tank for longer so that the particles have more time to settle to the bottom. Anyway, that's primary sedimentation. Then we can come to secondary treatment, and that's where we go back to the bacterial activity. And I mentioned this already. So I said last time that there's different environmental conditions that you need to ensure you have or don't have if you want or don't have bacterial activity. So here in the secondary treatment, we want to have bacterial activity because we want to grow as many possible bacteria that we can, so that these bacteria consume and therefore reduce the biological loading in our water, so that this biological loading is not then discharged into the receiving environment. So the primary treatment here is, the primary function of the treatment is reduction in BOD. Reduction in BOD can be achieved aerobically or anaerobically, and I mentioned this already, that you have anaerobic treatment for the sewage sludge. For the secondary treatment, you use aerobic treatment. For the sludge treatment, you use anaerobic treatment, and we'll get to that in a very short while, why you use these different things. One thing maybe to mention is that with all of these, the reduction in some specific compounds really only happens after the bacteria adapt to the substrate. So that's again my celeries and what was it now, fried Mars bars example. You can apply this to anything. The bacteria as a cohort are very diverse. There's thousands of different bacteria in there, and they can also adapt. They can mutate to a degree. So if you expose a good mix of bacterial sort of population to a wastewater and you give it time, then there's a good chance that the bacteria will adapt or specialize to treat whatever you have. But all that takes time. So what you have in a conventional wastewater treatment plant is you have highly digestible material coming through all the time, your fried Mars bars. So a conventional wastewater treatment plant, therefore, is not particularly good at dealing with maybe specific compounds that only happen on a Thursday afternoon or something like that. So if you want all that stuff to be treated, then you need to allow bacteria to adapt. Otherwise, all they do is they remove BOD and they remove the short BOD. So they're really good at removing BOD1, BOD2, BOD5. BOD25, you don't get much removal in the sewage treatment works because the water just doesn't stay in there long enough. The bacteria don't have enough time to digest the stuff, and they constantly have the attraction of the new, easier to digest stuff coming through the plant. So I keep talking of aerobic and anaerobic, and now I'm talking of aerobic, anaerobic, and anoxic. And some of these terms are not particularly very intuitive, I think. So let me just indulge myself for a short while. So it's sort of in the name and it's sort of not, because the names were developed historically and not necessarily all that well descriptive. But what you have here is the aerobic treatment, and that sort of comes out of the Greek word for air. And it really means this pen is doing not very good things here. Aerobic treatment is reliant on oxygen in its gaseous form. So that's the oxygen that we have in the air, O2, and that's why it's aerobic. So it refers to air, yes. These are the bacteria that you find in the conventional wastewater treatment and the secondary sedimentation. So aerobic bacteria are secondary treatment. That's what you have in secondary treatment. You have the bacteria, you have the waste, you add lots of oxygen into the tank, and then these bacteria grow away and do the stuff. Then you have the other big category, which is subsplit into two, which is anoxic or anaerobic. So that's where it gets a little bit fluffy, I think. So anaerobic bacteria are the ones that do not need air, so they do not need O2, but they actually, you have to go a step further, and they say that they really, yes, absolutely, I get to that in a minute, facultative. The anaerobic bacteria do not tolerate oxygen. So if you want to operate an anaerobic treatment plant, then not only do these bacteria not need the oxygen that comes out of the air, but they do actually get inhibited by molecular oxygen. So anaerobic bacteria are really quite fussy about this sort of stuff. Anoxic bacteria are different in that they really are facultative. So what we have here is we have sort of the strict strands. You have some bacteria that are only aerobic and they only function in the presence of oxygen. You have anaerobic bacteria that are strictly anaerobic, so they do not function in the presence of oxygen. And then you have the facultative strands that can switch between respiration, between aerobic and anoxic. So this is where it gets a little bit fluffy. So anaerobic digestion is AD, no oxygen. Aerobic digestion relies on oxygen and needs therefore air or other forms of oxygen supplied. Anoxic bacteria are a little bit of a mix. So I'll try to write this. So, I can't even spell anoxic. So they have two ways of operating. They can use oxygen, and if they are in the oxygen form, if you want, or in the molecular oxygen form, then they function in the same way as aerobic bacteria. So I know this is not biologically correct, but for the function of a sewage works, it is. So if you have anoxic bacteria and you give them molecular oxygen, then they function as if they were aerobic. So they will take BOD and they digest BOD and remove it from the sewage works. That's what they do. If you take the oxygen away, then they become anoxic. So they switch to the anoxic function. And what this means is that they still use oxygen for respiration, but they use different forms of oxygen. We can come back to that later, but maybe let me just say here for the moment, what they'll do then is that they can use the oxygen in something like NO3 minus. So that's nitrate. And in the nitrate, you have here some oxygen molecules. And what these anoxic bacteria can do is they can utilize the oxygen that's in the nitrate for their respiration. So they can reduce nitrate to nitrite. So they removed one oxygen atom here out of the molecule. NO3 becomes NO2. That means they have one oxygen molecule atom for oxidation processes. So that means that anoxic bacteria, if you switch the air off, they don't breathe, like simpleton for me, they don't breathe air anymore, but they'll breathe nitrate. And that means they reduce nitrate to nitrite and so on. And that actually is what we call denitrification. And that means that anoxic bacteria, the main role of anoxic bacteria in the sewage works is to denitrify the water. So that is the removal of nitrogen, and I'll come back to that at a later stage. I personally find this complicated because it's not really that well described in the names, but if you wanted to remember it this way, aerobic bacteria need air and won't function well without air. You have sort of facultative strands within the aerobic bacteria that can also switch their respiration to other forms of oxygen, particular nitrogenous oxygen, so they can start breathing nitrate. And then you have the anaerobic bacteria, which do not rely on oxygen at all, and for whom, in fact, oxygen in its molecular form, it's inhibitive. So anoxic and aerobic bacteria, they're sort of related in a way. You find them in the same treatment plant, in the same tank. Anaerobic bacteria, you will probably not find close to aerobic bacteria because they really are completely different kettle of fish. So there's a few things here in the chat. Yes, it depends on the type of bacteria, and facultative bacteria will stand in both conditions. Yes, with or without oxygen, if we specify that and say with or without molecular oxygen, so they can survive with oxygen that's bound in other molecules, but not the sort of O2 molecule. Anyway, these are the main forms of bacterial digestion that we use in sewage works. And then very briefly, I don't want to go into that detail either, but the main difference is in the metabolisms, that the aerobic bacteria, like it says there in the name again, they use oxygen and they turn oxygen into carbon dioxide and water. So that is your conventional, whatever you want to call it, incineration. That's what happens in our bodies. We breathe in oxygen, we have some food, we add oxygen with that, we create carbon dioxide, water, and of course we also create energy. That's what we use the stuff. We burn it, so we get energy out of it. And another thing that's missing there is biomass, because we grow, or the bacteria grow. So some of the energy that they get out of this, they turn into biomass. So that's what happens with aerobic bacteria. Anaerobic bacteria, and I'm not going into anoxic here, are very different in that you see different steps here, 3 steps. You could also break this down if you wanted to in 5, 6, or 27 steps. Depends how far you want to go into the biochemistry. But for me, it's either referred to as 3 steps or 5 steps. If we stick with a simple one, just for the purpose of describing what happens in anaerobic digestion, then really what's happening is that long chain hydrocarbons get broken down into shorter chains. These shorter chains get turned into very short chain fatty acids, and the very short chain fatty acids in the 3rd stage get turned into methane. So those are, to me, the 3 main sections, and there's permutations amongst this. So long chains go into short chains, and short chains go into go into methane as the end product. So the final outcome of anaerobic digestion is that you have some sort of organic substance, whatever chain length, so don't time me down on the C number here, will be converted to methane and carbon dioxide. So that's just one thing to say, that on the side, if people say to you that, oh yeah, aerobic treatment isn't good because it releases carbon dioxide, so does anaerobic treatment. The main difference is that anaerobic treatment as the main product has methane, whereas aerobic treatment as the main product does not have methane but has a lot more energy. So if you look at it just like this, say these are aerobic, anaerobic. Aerobic bacteria need oxygen, and that actually we could also say they need energy, because in order to get that oxygen here into the water in the sewage treatment works, you need to have pumps, blowers, stuff that somehow constantly replenishes the oxygen consumption in the water, and that takes a lot of energy. So the operating cost of a treatment plant is predominantly aeration. The pumping and so on is not the big thing. And most of the cost that comes from treating your wastewater is the supply of oxygen. Therefore, most of the carbon footprint of wastewater treatment is the supply of this oxygen for the aerobic treatment. So we produce nothing, carbon dioxide, water, biomass. Let me just put on here biomass. This is actually then the same as sludge. Yeah, that's the sewage sludge, because the bacteria keep growing. And sludge is another problem. Really what we're doing is we're taking, I don't know, human poop and potato peelings and whatever, and we're turning that into sludge. So we're creating one problem by getting rid of another problem. The ratio here roughly is 50%. And again, don't say all is said, it's 50%, which means that for every 100 gram of energy worth of your fried Mars bars that goes into the sewage treatment works, you get 50 grams of sludge, because that's what the bacteria do. They take the fried Mars bars, they add oxygen, bit of carbon dioxide, bit of water, bit of energy, and biomass. And about 50% of the energy, maybe 45 more, is converted into sludge. So aerobic treatment on the face of it is actually not very good, because you need to add energy, cost, carbon to make the process work. And all that you're achieving is that 50% of the biomass of the BOD is reduced, and the other 50% is converted to sludge. So that's a lot of effort for something that's only 50% efficient. Anaerobic treatment doesn't need oxygen, so you don't need to pump air into it, you don't need to spend energy, and it gives you methane. So it converts the waste into something that we can then maybe turn into biogas and fuel our cars with or whatever. So that would, on the face of it, be much better. Still, in conventional wastewater treatment, secondary treatment is aerobic, and is only aerobic. There's lots of work being done, and we tried it ourselves as well to see whether you cannot use anaerobic treatment for that. The main advantage of this stuff is that it is stable. So aerobic treatment stable, anaerobic treatment is tricky. Another highly technical term here. It's tricky for starters because you have 3 different stages. So it's not just one type of bacterial function that you need to concern yourself with, but it's 3 types of bacterial functions. And like with any good chain, the chain is only as strong as its weakest link. And the weakest link is this one here down there. That is what gives us the problem. So if you have anaerobic digestion and it is for whatever reason inhibited, then the step that normally is inhibited is this last step here. So the conversion of fatty acids into methane and carbon dioxide normally gets disturbed first. And if you think that there's constantly stuff flowing through and more waste being put into anaerobic digestion, if you take this last step out of this, then really what you have is that anaerobic digestion produces fatty acids. So that will change the pH. So the pH will go down. And if you have inhibited anaerobic digestion, what you'll see is that the pH drops, so the stuff becomes more and more acidic. Now, the problem with a drop in pH is that a drop in pH more and more inhibits this last step, so it's a self-perpetuating step. Once you see the pH drop in anaerobic digestion, you've pretty much had it. It's very hard to recover from this. And then eventually the whole thing stops. So in a nutshell, anaerobic digestion is tricky. It doesn't deal well with changes in substrate. It doesn't like, lots of food in the morning, not so much in the evening. It wants a steady feed. These bacteria, particularly the last step, they're quite tricky. They're sensitive to inhibitants. So they don't like the domestos and all the sort of stuff that we throw into our toilets. They get stopped easily, and then the whole process stops. So in wastewater treatment, what arrives at the sewage works, you don't really know what comes down the pipe. There certainly are changes day and night, morning, afternoon. There's changes depending on the day of the week. If you go to small sewage works, you can literally, if you stood there, you could see the time of the day if you had nothing else but the water flowing. Because at, 6 o'clock in the morning, the first people get up and they have a shower, they go to the toilet and they make the tea. And half an hour later or an hour later, depending on how long the type is, you can see the water level rising. And that means there's a change, even diurnal changes in the quality of the water. Aerobic bacteria are quite happy with this, and you can just switch the blowers on a bit more and give them more oxygen, and they'll just consume it all. They're tough. Anaerobic bacteria don't like this. So that's why anaerobic treatment, even though it looks possibly better in terms of carbon balance, is not normally used in secondary treatment in wastewater treatment works, simply because it is too complicated. And as a side, that's why it is used in sludge treatment, because with the sludge, you have the sludge, you control the sludge, you have a big tank of sludge, and you feed that constantly into anaerobic digestion. There's no change in consistency or substance because you're taking it from a big buffer tank, and the happy anaerobic bacteria will reduce the BOD that comes from secondary sludge very easily and turn it into methane. Anyway, I'm putting a lot of concepts together in one here. So let's maybe step back a little bit and go over this same stuff in a different form. So the difference in performance, if you're having pie charts and they're very crude, anaerobic, aerobic, then you see what happens with the energy really that comes from the waste material. You have lost heat energy, and there isn't much difference between aerobic and anaerobic. So you can see here that this pi piece of lost heat energy is about the same for both of them. Then you have synthesis, that means the buildup of body mass. You can see that that's really quite small in anaerobic digestion. So anaerobic bacteria, I think of them as the sharks of the wastewater treatment world. People say that sharks are sort of waste hoovers. They eat a lot of stuff, but they don't actually get much energy out of it because they just put it through the bodies and make it small so that other people can access it. People, other animals. Aerobic treatment, you see here that aerobic treatment is big on synthesis. So I said earlier on 50%, but here this pie chart would more suggest maybe 45% of the energy that goes into an aerobic treatment plant is turned into synthesis, and this here means biomass. So that's bacterial sludge. So that's what I said before, 45–50% of your Mars bar gets turned into sludge. Then you have respiration. So aerobic treatment, produces a lot of carbon dioxide. Anaerobic treatment doesn't produce a lot of carbon dioxide. You see one of the big disadvantages of anaerobic treatment is here unused. So anaerobic treatment is not particularly good, that's negative, at digesting everything. So aerobic treatment tends to give you better removal rates. And then the big advantage of anaerobic digestion, of course, is this: end products And this is in terms of energy, because this here is your methane. So you get about 40% or 45% of the energy that's in the BOD, in wastewater, converted into methane. That means the methane can be burned easily, and it means that something that was previously dissolved in the liquid matrix, which doesn't burn very well, you put that through anaerobic digestion, and you get about 45% of the energy contained there in the form of biogas that you can then easily use. So again, anaerobic digestion much better in terms of carbon balance, but it's fickle, it's tricky, not easy to run. It needs continuous or constant conditions. Not good for dealing with change. Aerobic treatment is not very energy efficient. It gives you a secondary problem of lots of biomass, but it gives you really good removal rates, and it's stable. And that's why aerobic treatment is used in secondary treatment, and anaerobic treatment is used in sludge treatment. Because the sludge, I keep repeating myself, but the sludge is stable. You can feed it at the rate as you want, and there aren't any surprises in it, because the sludge is really nothing else than these aerobic bacteria bodies, biomass. So all the whatever pharmaceuticals, pesticides, antiseptics that we put into our wastewater, they were affecting the aerobic bacteria that are fairly unaffected by it. So they still grow, build up biomass. So the biomass of the aerobic bacteria tends to not have all the stuff in it that we throw in the wastewater, because it's just biomass. So the biomass here is relatively free of all these inhibiting substances that we throw into the water. And that's why anaerobic bacteria can digest this biomass relatively easily, because it's not contaminated to the same extent as the original pure wastewater is. So that's why you would normally not find anaerobic bacteria on a conventional treatment works, and you would only find anaerobic digestion in the sludge treatment of treatment plants. So that's the secondary treatment done, which tends to be the aerobic treatment. There was a quick side stint onto anaerobic treatment, as in sludge treatment. And then I'd like to look at the anoxic treatment a little bit more in the context of the whole biological treatment. So going back over the biological treatment, what it does is primarily BOD removal. That's the main aim why it was introduced all these years ago, that we want to get rid of all the material that has an oxygen demand or generates an oxygen demand that would be negative for the receiving water. Then it can also do nitrogen removal, and this is where the anoxic bacteria come in. So if you look at this in a little bit more detail, what you find is that nitrogen enters sewage works primarily in the form of ammonia. It could also be urea, but that doesn't really matter quite so much. So say ammonia, NH4+, and you have the nitrifying bacteria. So this is the aerobic part. The nitrifying bacteria, because they work on aerobic digestion, as in incineration, if you want, oxidization, they add oxygen to the nitrogen. So NH4 turns into NO2 nitrite with some steps in between. Let's not worry about them just now. And then the NO2 nitrite gets further oxidized to nitrate. And that's the end of the aerobic treatment. So this aerobic treatment is called nitrification. And it's looking like it says here, nitrifying bacteria. So the first step, that's the nitrification. I can't spell this, or my handwriting is too bad for this anyway. So the first part of this is nitrification. You're nitrifying the nitrogen from ammonia to nitrate. So you're adding oxygen to it. if you look at this in detail, and if you're familiar with this, then you know that this sort of stuff, nitrite, is actually hugely toxic. So you really absolutely do not want to have nitrite leaving your sewage works. So the conventional wisdom is to oxidize this completely and go to nitrate, because nitrate is not toxic. But you will also know that nitrate is still a nutrient. It is still a fertilizer. In fact, if you look at several commercially available fertilizers, bag fertilizer, then quite often you will have ammonium nitrate. So ammonium nitrate is a salt out of ammonium and nitrate. So in terms of fertilizer removal, you have not achieved anything by oxidizing in an aerobic treatment ammonia to nitrate, because you still had one atom of nitrogen, and at the end of the whole treatment you still have one atom of nitrogen, and it's the nitrogen that is the fertilizer. It's not the oxygen or the hydrogen. So you haven't achieved anything. The only thing you have achieved is you have reduced acute toxicity. Ammonia, for example, is really toxic, acutely toxic possibly, to fish, amphibians and so on in water, and you can see this or experience this yourself if you use sort of ammonia-based cleaning agents. Sniff them a little bit and they burn your mucous membranes. So the same happens to fish. The stuff just isn't very good. It gives you, it affects your tissue. Nitrate has the same fertilizing capacity as either of these other two, but it also is toxic. So we don't want to use nitrite. And then nitrate only is the fertilizer, so it's not toxic. So all you have achieved by oxidizing this stuff is reducing toxicity, but not reducing fertilizer capacity. If you want to really truly remove the fertilizer, then you have to have the second step, which is the denitrification. So you then reverse what happens here. You're trying to get the oxygen out of these molecules, and the steps tend to be from nitrate back to nitrite, then to NO, N2O, laughing gas, and then back to dinitrogen. So just if you go fully down this route, then the dinitrogen will escape as a gas, and it will simply go back to the 70 or whatever percent that our atmosphere is made up of, nitrogen as a gas, molecular nitrogen. So this stuff is inert, doesn't have any fertilizer capacity, it's not toxic or anything. We breathe it all the time, and our plants don't grow faster because they grow in it. So after denitrification, you have achieved the removal of nitrogen from the water, because if you look through this all the way along, nitrogen is in the water. And at this last step, the nitrogen is converted into gas, into the atmosphere, is out of the water, and it's inert. The eagle-eyed amongst you will know that nitrous oxide is also a gas. So nitrous oxide might escape into the atmosphere as well. In fact, it's relatively easy to create nitrous oxide because it normally is a byproduct, particularly if there's some inhibition. So if this last step is inhibited, nitrous oxide can easily be generated. We don't want to do this because nitrous oxide has some 300 times or so the global warming potential of carbon dioxide. So it is a really, really super potent greenhouse gas, and you do not want to release nitrous oxide into the environment. In fact, there's a lot of research going on to avoid this. Problem in a way is that it's very hard to measure what happens exactly in a sewage works, and conventional monitoring will only do one or two things. It will measure ammonia in water. So if you measure ammonia in water before and after a sewage works, and if you find that the ammonia is removed at the end of the treatment, you might say, hey, we have achieved nitrogen removal. But all you might have achieved is the creation of nitrate. So really you have to measure ammonia and nitrate. And if you have no ammonia and no nitrate, then you might say, oh yeah, I have achieved my aim, but you may also have generated nitrous oxide. So what I'm saying is that really to fully understand what happens, one should measure ammonia, nitrate, and nitrous oxide emissions, because you want to avoid these. And then equally, some of you will have spotted that this stuff here, NH4. So normally what you have is you have, oh dear, this is terrible, isn't it? NH4 plus is in an equilibrium in water with NH3, and it depends on the pH. So if you change the pH, then you're influencing this hydrogen ion here. And if you move the pH and you drive this equilibrium towards NH3, then NH3 is a gas, and that could also easily escape. So one way of getting rid of the nitrogen in water would simply be to blow lots of air through it, and guess what we're doing in a sewage treatment works? But that would really only work if you have ammonia rather than ammonium. So one way to get rid of the nitrogen would be to strip it, but that obviously wouldn't be very good, because really what you're doing is you would create acid rain, as we used to call it a lot. So that is the deposition of ammonia from the rain. And obviously what would happen with this is that the ammonia would go into the atmosphere, but at some point it would get absorbed by water in the atmosphere and or get removed back to ammonium, and further down somewhere in a field it would deposit again as NH4 plus, and then it would give you diffuse pollution in terms of fertilizer and toxicity. So there is another route to get nitrogen out of the wastewater by stripping it, but you don't want to do that, because the stripping really only leads to this sort of deposition somewhere else, unless you collect this properly, and so, but that doesn't normally happen on sewage works. So what I'm trying to say is the only way conventionally to get the nitrogen out of the wastewater is to use nitrification first with the aerobic bacteria, and then denitrification with the anoxic bacteria, or it could be the same bacteria here. The only difference is in terms of process conditions, that here you add oxygen, and then here you don't add oxygen. And all that could mean in a treatment works is that you have a tank where the water is being treated, and you have the blower on for an hour and a half, and then you switch the blower off for half an hour, and then all the oxygen is being consumed, and all of a sudden the bacteria find themselves without oxygen, and the facultative bacteria will then switch their respiration from oxygen to nitrate, like I said before, and they will use nitrogenous oxygen for the respiration, and thereby denitrify. And I'd like to say a little bit more about that. Well, I don't know if we do it today or next week, but there's one or two process conditions alongside this that need to be taken into account. The one important thing is that the oxidization of nitrogen will happen only after the BOD is used up. And that's the same sort of thing as the celery and the fried Mars bars. The BOD has quite high energetic value, so bacteria take a lot of energy out of digesting BOD. Banana peel, fried Mars bars. They can also digest the nitrogen in nitrification, but there isn't the oxidization of ammonia to nitrite and nitrate doesn't give much energy. So the bacteria prefer not to digest ammonia because they don't get so much out of it. And that means that nitrification happens only after all BOD is used up. So you really need to have quite complete BOD removal before you get nitrification. So that means if you have a sewage works where you don't supply enough oxygen, or where there's too much BOD, or maybe where the flow is too fast and bacteria don't have time to digest all the BOD, then you will not find nitrification happening. And that means that as an indicator, if you have NH4 plus in effluent, that is an indication for incomplete treatment. Because if you had complete treatment, then all the BOD would be digested, and then the ammonia would be digested. If you see ammonia in the effluent of sewage works, then that's a surefire indicator for that there's something not quite happening here. It's either too much waste going through, there's too rich waste, bacteria inhibited something. So NH4 measurement in the effluent of treatment works is a really good quality indicator overall for the functioning of the biological stage. Right, I'll come back to this. I know this is quite a lot, especially if you're not into biology. First, recap the whole thing. You've seen this before 2 or 3 times, so hopefully by now it makes sense. Your grit separation, just the very coarse organic, inorganic materials, sand, grit, stones, goes into waste, and this is actually inert. So it tends to be just sand and so on. But it could, of course, there could be some organic material in it, but it tends not to be. So what comes out of the grit separation is inert waste. What comes out of the screens tends to be organic waste because it's sort of twigs, leaves, toilet tissue, sort of paper material, cellulose. So that you could put that into a different skip if you want to save money on the waste disposal. Then you have the primary settlement where you remove BOD in the form of solids just by sedimentation. Then you have the biological process where you remove BOD in the form of primarily, I need to practice more writing with this pen, in the form of soluble materials or very finely dispersed materials. And what you get out of that is a lot of sludge. So this sludge you're holding back here in the secondary settlement where the bacterial biomass is collected at the bottom of the separator, goes out into sludge treatment. Or like I said before, some of it could be recycled back into the biological process so you ensure that you have enough bacteria. And the sludge treatment tends to be AD for reasons you discussed earlier on, or thermal recovery. Those are only the two options left these days. So turning it into breeze blocks and all this sort of other stuff doesn't really happen very much, with the big exception, of course, of land application. I haven't said much about this, and other than saying that in Scotland about 50% of sludge is applied to land. In the UK as a whole is about 80%. The benefit of that is that you put the organic material to soil, so you're replenishing the soil with organic substances and fibrous material and whatnot. You're also adding nutrients to the soil that otherwise you have to pay for or spend lots of energy to get them out of the atmosphere. But the big problems with the land application is that you're adding a lot of material to the land that you don't quite know what's in it, so all sorts of micropollutants and so on. The other big problem with land application is not Her Majesty the Queen, but heavy metals. And the heavy metals come quite naturally in sewage treatment because the sludge, if you think of it, is nothing else but the biomass that's being generated in the biological process. And biomass, the same as you and I, at the bottom of protein in particular, you tend to have a metal ion, which gives the 3D structure to the protein. So if you're digesting the organic parts of a protein, what you're left with is a metal ion. So that's exactly what happens here. You grow all these bacteria, you concentrate them, you put them through anaerobic treatment. That removes the organic fraction of the biomass and you're left with heavy metals. So sewage sludge just is quite rich in heavy metals naturally, if you want. There's nothing you can do about that. It's just the nature of the beast. So none of this treatment, none of that treatment, pretty much no treatment whatsoever is available to remove the heavy metals from sludge. So when I say that the issue with sludge application to land tends to be around the uncertainty of all the substances that may be in the sludge and what they do to the land and what the toxicity is and so on, there's certainly no uncertainty about the heavy metal content of sludge, because sludge does contain a lot of heavy metals. And you can do fairly simple calculations, and there's maps available that tell you how long sewage sludge can be applied to land so that you use the benefits of it. So you say, how much nitrogen does my plant growth need? How much organic biomass do I need? And you apply the sludge accordingly. And then you end up with projections that would say something like, I don't know, between 50 to 100 years of sludge application to land would lead you to a situation where the continuous application of heavy metals leads to a sort of steady increase and accumulation of heavy metals in the soil, so that after 50 years of application, the soil would be so rich in heavy metals that it is contaminated. You would see negative effects. So the sludge application to land, while still a possibility at the moment, is certainly not something that is, an unlimited outlet route, because eventually, discounting everything else about micropollutants and so on, eventually you will get to a stage where there's so much heavy metal being put onto the land that the land becomes over-enriched with heavy metal, and we'd have to stop it. So land application is still very important for sludge disposal, if you want, or utilization. But in the sort of medium, long term, whatever you want to call it, land application will not be an option anymore because of the continuous stream of heavy metals. So the only options that we have really long term are anaerobic digestion and thermal recovery. And I think that's what you see more and more, that these two things are being developed, possibly in combination, that you first put the stuff through anaerobic digestion, and then what's left after the anaerobic digestion, you dewater that, and then you put that to thermal recovery. So anyway, that's the general layout of the plant. I'd like to say just one or two things to go away from all that technical stuff about who pays for it. And then for the next hour, I'd like to go into more details. So I'd like to talk a little bit more about the nitrification, denitrification, and maybe a little bit more about other tertiary treatment. So we can pick that up then. And then finally go into, for the fourth hour, go into sort of more design criteria, particularly for small applications. So you can have this overall treatment plant. That can be a treatment plant that treats the waste of, I don't know, 1 million people. But this could also be, a plant that treats the waste of 5 people. If you're thinking of a little hotel or a holiday lodge in the national park in Scotland, still you need to have all these functions in there. So I'm going to talk a little bit about that. So Phyllis just had a question on the chat. Can the heavy metals not be treated out? Binding them into insoluble compounds that can be precipitated? Yes, absolutely. All the stuff in theory is possible. The practical problem with this is that the sewage sludge is still very dirty and enriched with all sorts of other material. So by the time you start binding them, you're collecting a lot of other crud, technical term here, and that makes the separation of the metals quite tricky and inefficient. And the other big thing is that these heavy metals is not just maybe the ones that we are worried about, I don't know, mercury and chromium and stuff, but you also have an awful lot of iron in there. So if you're talking about sort of ion exchanges and resins and heavy metal traps and all this sort of stuff, a lot of this will be taken up with iron. So it's actually very hard to remove the metals that you really are concerned about, that give you the toxicity, versus maybe iron or maybe even a bit of copper in there and that sort of stuff. All that stuff will conflict your process. So technically, yes, can be done. Practically, it's too expensive, simply because the process is not fine-tuned enough towards those heavy metals that you really are concerned about. It captures all the heavy metals, and you do all this in a really, really still quite dirty matrix. So absolutely correct, can be done. Too expensive, too complicated, doesn't work good enough. It's cost-benefit problem here. Okay, so like I said, if I'll pick all this up again in the next session. So if you wanted to maybe read up on a few of these things, particularly nitrification, denitrification, I'll go over nitrification, denitrification again in the next session, particularly in the context of how can we trick the bacteria into switching oxygen off, switching it on. What's the best way of dealing with this? And then in the section after that, we go a little bit more into how does this apply in practice. So just one other aspect about who's paying for this. Don't know if you've heard about this, but people pay for the wastewater treatment. So in Scotland, in the UK, if you are lucky enough to rent or own your own flat, not student accommodation, then you pay council tax. And as part of the council tax, you also get charged a water tax. So the water tax is roughly half for the supply of fresh water, chan stuff, giving you clean drinking water, and roughly the other half is for the privilege of taking your wastewater back off you, putting it through all these treatment plants, and then safely discharging it back into the environment. So if, like I said, if you're paying, if you're a private individual, so if you, I don't know what's the best word, if we say if you're a citizen, then you pay, and you probably don't even know you pay, and most people don't because it is part of the council tax that you get. In other countries it's different, you pay differently, separate bills from the water companies and so on. But you're basically paying for the wastewater, and you pay pro rata. So the pro rata in the UK is slightly odd in that, well, in Scotland anyway, it's slightly odd in that water is seen as a common good and it's available to everybody, and you don't pay by how much you use fresh water and by how much you use the wastewater treatment service, but you pay by how expensive your house is. So the argument is, I guess, that if you have a more expensive house, then you use more water. Quite whether or not that's true, I don't know. I guess the Queen has a fairly big house, but, you know, and I guess she uses a lot of water because lots of people are living in the house. You could have a big house with 5 people in it. You could have a big house with 1 person in it. You pay the water charge based on what the council tax band of your house is. In the UK as a whole, people are now going much more towards metered supplies, and I think that's something you find quite a bit over Europe, and every country does it differently. But basically, there's some sort of paying pro rata on a flat fee. And for citizens or for municipal discharges, there is no worries. So you go to the toilet, you flush the water, you pay a bit for it by whatever rationing or apportioning, but you just pay for it and that's it. If you're thinking of companies or businesses, that's slightly different. So if you're a business, then you need to really apply, you need to get permission. And that sort of comes out a little bit out of this sort of polluter pays principle or something. So I think everybody would agree that you cannot stop people to go to the toilet. Yeah, that just can't be done. You can't stop me doing this. Or you could try, I might work for 3 days and then I die. So nothing you can do about it. Municipal wastewater just has to be accepted and will be treated, and you charge for it. That's it. For businesses, it's a different story, because a business, you could argue, does not have to produce waste. You could say that a business might operate in different ways, that it can reduce the waste or completely avoid the waste, put it somewhere else, whatever. So basically you need a permission, because it's always optional for a business to operate in a certain area and in fact to do the business. So you need permission for this. And that means that in the UK anyway, what you would call this permission is you get a discharge consent. And that could be something quite simple. So if your business is whatever, a card and gift shop, then this card and gift shop would be characterized by having wastewater that is very, very similar to municipal wastewater, because all you would produce is the wastewater that comes out of the tea kitchen of your employees and out of their normal employee toilet. So that would be very similar to municipal wastewater, to normal citizens' wastewater. So that means that for these business users that don't have any particular and are municipal-like, the discharge consent would simply be that the water company says, we put a meter in your house or we measure it, however, and you basically charge for the consumption. And we don't look at the water in any more detail. And that is what happens across most businesses, because most businesses do not have particularly toxic, high volume or whatever wastewater. So the university, for example, also does not have any particular measurement. They simply measure how much water goes in and they charge us for that. Very similar to what normal people get charged. But other businesses may have particular wastewater discharges. So say if you're a brewery, you produce particularly organic, rich wastewater, maybe in batches, so that you have quite sort of fluctuation in your discharge pattern. If you're a dairy, you have very rich wastewater that goes out. If you're a chemical plant, then there's maybe chemicals in the water. You get the picture. So for those businesses that are non-standard and don't produce something that is alike to normal people's wastewater, there's the Mogden formula. And the Mogden formula is basically a calculation of the cost that you pay as a business for discharging the water, and that cost is calculated based on the regional conditions and requirements and maybe limitations. So if you operate as a business in an area that has problems with nitrogen in wastewater or in groundwater more, then in that area, there will be a higher emphasis on removing nitrogen from the wastewater. So the water treatment company would be quite right to charge you more for nitrogen content, because they're trying to reduce nitrogen. So they have to spend more money on reducing nitrogen. Therefore, they charge you more. In another area, they might be more concerned about the volume of wastewater, maybe because their tanks are too small. So they charge you more for the volume. So you're seeing the theme coming up here. The cost of wastewater treatment is a combination of, and you hopefully not going to be surprised here, of a factor that is to do with solids. So they charge you a solids index or something, which basically says what is the cost of removing solids in that particular area based on the area's requirements and needs and whatnot, times the solids concentration that you have in your water. So there's a solids charge. And then there is a charge on BOD, on biological content, because again, that's what the sewage treatment works too. They remove solids and they remove BOD. And then there is a charge on volume. So they're saying that you could have quite low solids, for example, then you don't pay much for the solids. But because you operate inefficiently, you dilute all these solids in a very high volume of water. And then the sewage works has to deal, with all this volume of water, have the size of the tanks and the treatment pumps and all this sort of stuff. But also there's some efficiency considerations, because if you dilute stuff into very high volumes of water, then it gets very hard to treat it. So in a way, there's a tendency to say you concentrate your wastewater as much as possible, because it makes it easier to treat. The efficiency of treatment is better if it's less diluted. So they charge you for volume, and they charge you for something else, And that's very similar to the charges for gas and electricity and whatnot. They charge you for connection. So they say, well, there is a service, there's a network that we're operating and that we're offering you. So you get charges, standing charge for the connection. So these four elements together are the Mogden formula. If you're interested in that, Google it up. There are statistics across the country. And if you're a business, then you can check out in your local area what the elements of the Mogden formula are. So the Mogden formula applies throughout, but in Scotland or in East Renfrewshire, there might be a different charge for solids versus BOD, volume and connecting charge, than there might be in East Lothian or something, simply because they have different environmental conditions to deal with. So that's the cost. What you see here missing, I would say, is, so what we don't have is pollutants, other than BOD or solids. So there is no charge in principle for, I don't know, discharging pharmaceuticals into the wastewater. There's no charge for reducing chromium. There's no charge for having pesticides effluent from agricultural businesses or something. So you cannot, there's no polluter pays for pollutants as such. And in a way, that is possibly a problem, because I would say that the more toxic the water is, the more people should maybe charge for it, rather than just worry about how much BOD or volume there's in it. But that doesn't currently exist. And what's also missing is anything about the pattern. So I mentioned breweries before, or any other processes where you have batch operation. So if you produce a lot of water at a certain time and release that all at the one time, then you will have a very high volume all of a sudden, a very high BOD loads, solid loads, pollutants loads, and so on, that might temporarily overwhelm the treatment works. So a lot of that stuff then will be discharged into the receiving water, simply because the treatment works is overworked. So I used to work for Meat and Livestock Commission, so that was a trade body, and they had their own animal farms. And on one of the animal farms, the way it grew historically is that they didn't actually have land close to where the farm is. So they collected all the animal slurries, and when they changed over the stables, they discharged all this slurry, whatever you want to call it, at the one time. So whenever that happened, the local sewage works was completely overwhelmed and discharged pretty much raw, untreated wastewater into the surface water. But there's nothing they could do for that. My boss used to say, oh, we just pay more. But they can't charge you more for it because it's not included in the Mogden formula. So things like this, like other pollutants and the pattern, that's only described. So the wastewater treatment organization company, actually in the UK, it's the regulator. So the wastewater treatment companies are also the wastewater regulators. In their discharge consent, they will not only tell you how much you pay for the stuff, but they will also tell you the sort of other parameters and limitations to the discharge consent that you get. So for pollutants, they will tell you which substances you are not allowed to discharge at all, or what the maximum concentrations, blah-de-blah, of chromium may be in terms of concentration, absolute discharge, relative discharge, as in how much concentration do you have on any given day. And that's where we're going into the pattern. They will also tell you how you can time your discharge, whether they prefer to have it evenly over the day, or say you are that brewery and you produce a lot of BOD and high volume of water every 48 hours or whatever, then the wastewater operator might say, why don't you discharge this BOD and volume of water between 12 o'clock at night and 5 o'clock in the morning, because that's when all these fine citizens here tend not to go to the toilet and the plant is running almost idle. So rather than discharging all of this stuff at the same time that the citizens wake up in the morning, go to the toilet, you discharge it in the middle of the night, and then we have a leveling out of the load. So all these things are described in the discharge consent, and that's sort of a legal binding document that a business has to adhere to. So that's the interesting thing. For a business needs permission to discharge. The sewerage undertaker could principally say that they're not taking the wastewater of the business. There's no legal requirement to take it. They have to take private households wastewater. They don't have to take business wastewater. But there is, of course, an obligation in a way to take it, because if none of the sewage companies would take business wastewater, then we would have no business operation, or very little business operation, because without getting rid of the wastewater, it would be quite hard to run the businesses. So they're trying to avoid this, but this is a perpetual problem with, if you ask somebody from Scottish Water and so on, they always have problems when there's new developments, new housing estates being developed, or new industrial estates, or the government gets a big new industrial company to settle in the area. That is a problem for the wastewater companies, because all of a sudden they might find that they don't have the capacity to hold or treat the volume, or there's too much BOD, too much solids, whatever. And then they might have to build a completely new treatment works, and that's very expensive. So it's that sort of, a little bit extra might just tip them over the edge, and that's where then they either have to reinvest, and they could charge that back to the businesses, or they might have to just say, look, we can't treat it, or you have to pay extra or something. So if you are a business and you don't want to pay what the Mogden formula tells you, what options do you have? What can a company do? Have you got any ideas? Let me start a bullet point list here. If anybody has an idea, type it in the chat. But you run this new bakery, and you want to create a bakery in this rural village where there's only a small sewage works, and the sewage undertaker says to you, well, we don't really want your wastewater. We're going to charge you much for it. What could you do to reduce that cost? Yes, you can treat yourself, and many companies do that. There's a bit of a problem maybe in that, in the context of outsourcing and specializations and so on. If I'm a baker, then I want to bake bread. I don't want to worry about secondary treatment phases and all that sort of stuff. So it's a bit of a capacity issue, but you could treat it yourself. On the treatment, you have two options really. You could treat it for discharge into the environment, or you could treat it for discharge into the sewer. And that's, yes, the same sort of concept, but it's on two levels. If you treat the water yourself for discharge into the sewer, then all you're doing is you may be affecting the concentration of BOD or solids or volume or whatever, and you make it more palatable for the wastewater company. If that isn't good enough, you could decide to treat the water yourself and send it directly into the receiving environment. So there's absolutely no rule that says that business wastewater needs to be discharged into sewer. As a business, you can decide to treat all your wastewater to a standard that is the same as what the local water company would achieve, and discharge it into the environment. The problem with this is that then you're not dealing with the wastewater company as your regulating authority, but you're dealing with the environmental regulator. So if you did that, then you would need to get permission by SEPA on what you can discharge into the environment. Bob Gilmore will discuss that with you in more detail. So what we call this sort of thing, this regulatory control aspect here, means that SEPA, the environmental regulator in Scotland, would give a company a controlled activities license under the controlled activities regulations. So they would say to you exactly this: how much solids are you allowed to discharge, how much BOD, how much volume. No standing charge, obviously, but what SEPA would tell you would be much, much more detailed on pollutants and pattern. And they are possibly a much harder controller than a wastewater company. So most companies who treat themselves would basically do a little bit of pre-treatment, you might call it. So if the issue is about solids, they might reduce the solids. If the issue is about BOD, they might remove some of the BOD themselves and then discharge it to the sewer rather than going the whole hog. But both options are there. Okay, treat yourself. What else could you do other than treat? Any other ideas? You and your bakery? We don't want to treat the water ourselves, but it's the obvious ones. Yeah, you could try to reduce rather than treat. So maybe you could have a different process that reduces the amount of waste or the concentration of waste or whatever. Pattern of discharge. So that is maybe not always possible, but it is an option that you're free to take. Another thing that you could do also is you could, in theory, export. So you could say, okay, my waste is so rich and so toxic or whatever that the local sewage works can't deal with it. There's nothing to stop you from storing your waste and having a tanker come once a week or however often, collect that waste and ship it to an area or a treatment works where they have the capacity to deal with it. Obviously, that exporting costs money, so it's a question of money at the end of the day. What's cheaper? Is it cheaper to reduce or to treat or to pay the extra fees or something? But again, nobody says that you have to discharge your water into the local sewage works. You can take your water into a tanker and put it somewhere else. And then the really controversial one at the end, you could, of course, also say you stop producing this waste, yeah? Polluter pays and the rest of it. If you run a business that is simply not sustainable in terms of its environmental impact for the area in which you're running it, then the final thing of all of this could simply be that it's too expensive for you to create this waste, or that the description of your discharge consent means that you as a business are not viable anymore. Now that, of course, you could just imagine how this was go down in the press or something, that if Scottish Water destroyed 500 jobs by switching off the tap to a certain company or something. So that's not something that Scottish Water would like to do, but they can stop accepting your water, and they can stop you, or they can force you to stop your business by saying, we're not taking your wastewater anymore, and you have no permission to do anything else with the wastewater. So obviously these sort of things are maybe more palatable, better for business, but it could come to this. So the main message in that sense is wastewater of humans, citizens, individual people will always be taken, and the wastewater companies have to provide you means and mechanisms to take this water off you and treat it. The same does not apply for businesses. So businesses can be forced to shut down simply because their wastewater is too bad. And the only exception to this one is about wastewater of citizens always gets taken if there is a local sewerage network. So if I build myself a cottage on a piece of land that I was gifted on a croft somewhere, there is no local sewerage network, then I have to deal with that directly. And that means that then I as a private citizen have to also deal with the environmental regulator, because SEPA regulates all direct discharge of wastewater to the environment. So if I have a little croft somewhere and my own wastewater treatment plant, I need to record that with SEPA and basically get their permission to discharge. That's on a slightly different scale of control and regulation than it would be for a business, but it does still exist. So individual citizens, if they're not connected to a sewage network and want to produce wastewater in an area because they want to build a house there or something, they have to also get that license from SEPA. And that's the bit that I said we'll do in not next, but the session after that, how as a private citizen can I get to grips with, all of this sort of stuff. How do I build my sewage treatment plant that is sufficient so that I get the permission from SEPA to discharge straight into a river? Right, this is it for me for today. I hope that was not overly too confusing, and we'll go over this again and then go over it partially again. So hopefully at the end of that, it will all be clear. If you have any questions, let me know, get in contact.